Okay, so today's a really fun lecture. We've been developing algorithms for these edge disjoint path, minimum cut, and flow problems for the last two lectures. And maybe arguably the most nuanced algorithms we've done together as a class. And today we're going to see that there's actually many creative ways to use these algorithms and solve many basic problems. So, okay, let me just quickly review and help us warm up. Originally we're just interested in this question about kind of understanding how well connected two vertices were in the network. The applications I gave included infrastructure, CPUs, analyzing social networks, analyzing the World Wide Web. These are all natural, important networks that we want to analyze. Okay, and then there's of course many questions you can ask, of which we ended up focusing on these last two questions. What's the maximum number of edge disjoint ST paths and a minimum number of edges you need to delete to make sure S can no longer get to T? Okay, so these are also very literal applications of network analysis. Okay, so the maximum number of edge disjoint paths, I'm just trying to pack paths going from left to right in this picture. The minimum ST cut, I'm just trying to delete edges so that S can no longer get to T. And one very important feature about these two problems together is that at some level they are dual to one another. Okay, and basically a sort of big reason why we can even solve these problems is because one bounds the other, and in fact the optimum values are equal. The maximum number of edge disjoint paths is always equal to the minimum number of edges in any ST cut. Okay, so just to recap, one side of the duality inequality is somewhat easier. It was easier to argue that the number of edge disjoint paths is always at most the number of edges in any cut. So then we tried to get equality. To that end, we tried to develop some algorithms. The natural greedy algorithm, as we've discussed to death, doesn't quite work. Okay, but the key was to think about the fact that you can at some level reuse an edge you've already taken except in the opposite direction, knowing you can still extract paths later. So we had some kind of lemma for uncrossing paths. Oops. So that gives you ultimately the Ford-Fulkerson algorithm, which is pretty similar to our original iterative algorithm. The only difference being now that when we select a path, rather than just removing all the edges, we add back in the opposite direction. Okay, and somehow this is good enough to make it work. In fact, the proof was based on this idea that, in this residual graph that we're maintaining, at the end we can no longer get from S to T, in which case there's some set of vertices S can reach, and that forms the side of an S to T cut, the S side of an S to T cut. Okay, and we argued that that cut had the same size as the number of paths we took. And we already had that less than equal for free. So as soon as we got equality, then suddenly everything was optimal. I knew that I had truly taken the minimum number of edges in any S to T cut, and I had truly packed the maximum number of paths from S to T. Okay, good. We get all these very nice theorems. We got a running time that was proportional to the number of paths we packed. Okay. So last class we looked at that natural generalization where we added edge capacities. Now I can use an edge 5 times, 10 times, 100 times. Okay. Which raises a couple of issues. One is, of course, when the capacities are really big, our clever algorithms no longer polynomial time. The other is that if the capacities aren't even integral, then we had to extend our definition of path packing to allow for kind of fractional combinations, just weighted combinations. I can take 0.1 of a path, 0.2 of a path, and so forth. Okay. But structurally, not too much change. Up to scaling, up to clearing denominators and tricks like that. Our kind of max path packing is equal to the minimum capacity of any cut. Those theorems still held. Okay. The remaining issue was algorithmic. But before launching into algorithms, I introduced a third problem, maximum flow. This is sort of like a liquid version of path packing. Okay, if you kind of think of an infinitesimally small unit of path as maybe one particle is going from S to T. At some level, that's what max flow is modeling. Okay, so we still have capacity. So now I'm kind of assigning values to edges, sort of how many particles are going through an edge, how much flow is going through an edge. They still have to obey the capacity constraints. Okay, and then the other constraint was for every non-terminal vertex, what goes in is what goes out. Okay, so this is conservation of flow at the non-terminal vertices. Okay. Now, because what goes in is what goes out at all the intermediate vertices, ultimately the net flow leaving S, the starting point, will always match the net flow going into T, the terminating point, because where else can it go? Any other vertex it passes through, it has to pass all the way through. So at some level, we're injecting flow into the network at S, we're taking it out at T. And it's always equal amounts because the flow is conserved everywhere else. So that equal quantity, sort of the total amount I'm shipping from S to T, that's sometimes called the size of the flow. That's the quantity we want to maximize. The net amount kind of being transported from S to T. Okay. One passing comment is that this is our main canonical example of a linear program, insofar as I can actually write down just a math sort of equation with a limited number of constraints and variables. Okay, so although we like to think about it combinatorially, it's worth pointing out that this is also a simple mathematical problem. Simple in the sense that kind of the devices we're using, just linear equalities, linear inequalities, those are relatively simple as far as math goes. There's no quadratics, there's no exponentials, there's no funky other functions. Okay, so from a computational point of view, I'm just dealing with linear systems. That's what we mean by simple. Okay, so max flow, of course, seems very similar to path packing, and we made this rigorous, because in particular, we kind of showed that, the max flow is always at most a min cut. Moreover, any path packing can be turned into a flow of the same size. And you put that all together and you get that the maximum number of edges you can pack, in that weighted sense, is equal to the maximum size of any flow, which is equal to the minimum capacity of any S to T cut. Okay. And then the last part of our lecture, almost done with the recap part, was coming up with an algorithm for this max flow problem, which based on one of the PSO problems will also give you algorithms for weighted disjoint paths and stuff like that. You can take a flow and decompose it into paths. Okay. And what we did was a couple of natural ideas. We took our augmenting path algorithm and we made two changes. One is, well, once we found a path from S to T, we sent as much flow as possible. That seems natural. Why not? Okay. But the key part to getting the right running time was when looking for a path from S to T, we always picked the shortest one. Okay. So we always augmented along the shortest path from S to T. And that was really the only change to the algorithm. Okay. Now, what the shortest path let us argue was that for every vertex, if I'm kind of starting at S and I'm in a residual graph, edges get inserted and deleted, and there's always some distance from S. How many edges does it take to get to this vertex V? And we showed that because we're always going along the shortest path, and that dictates which edges get inserted and deleted and updated in a residual graph, V never gets closer to S. Over time, it only gets further and further away. That was sort of the key thing. And with that, we can argue that every time sort of an edge disappears from the graph, an edge between point A and point B, it disappears. So at that point, B was right after A. And later, if point A to point B reappears in the graph, I know that in the previous iteration, it was in the shortest path, so B was right before A. So every time an edge disappears and reappears, as we use up all the capacity, and we get back capacity from using the opposite direction, that implies that sort of A and B switch relative order to each other. Sometimes A is closer to S, sometimes B is closer to S. But because the distances never go down, every one of these reversals implied somebody has gotten farther away. Okay, so that's what the analysis was based on. It was just based on these distances, and in particular, compared to the original augmenting path, it's not like we were ever keeping track of how much flow I've already routed. Our analysis had nothing to do with saying something like, oh, I've already routed half of the max flow, 3/4 of the max flow, 5 units of flow. It was keeping track of these distances in some dual way. Okay, so that gave us an m²n algorithm where the running time is independent of the capacities, independent of the size of the flow, a strongly polynomial running time. All right, okay, now let's do the fun and new stuff. So we are going to talk about a bunch of applications of these subtle algorithms that we've been developing. Okay, so I put them in circles. So this is going to be all about changing the input today. I think all of these reductions are pretty clever. Maybe some are more straightforward than others. And our game plan is going to be, first I'm just going to run through all of them and introduce all the problems, which is a pretty diverse set. And then afterwards, one by one, we'll go through and try to figure out each one. Okay, and that's for two reasons. One, so that you can appreciate how many different things we can do by getting that snapshot early on. But two, also maybe to let you think in the back of your mind about some of the problems, having seen it at the beginning, so you can guess at the solution later. Okay, so this is one with lots of pictures. Okay, so here's one that many of you may have done in your PSO. I'm not sure if all PSOs got to it. This is more of an extension of max flow. Okay, so just like we had edge disjoint paths, we can also have vertex disjoint paths. So in this simple example, there's two edge disjoint paths from S to T. Right? Maybe say using the top edges and using the bottom edges. But there's only one vertex disjoint path because that middle vertex becomes the bottleneck. Okay, so small distinction. There's also a vertex cut of size 1. I can remove one vertex and disconnect S from T. Okay, so this is a very natural extension or variation of edge capacities. In general, vertex disjoint, I can think of that as capacity 1, but I can in general have lots of capacities on the vertices of varying amounts, saying kind of how many paths can go through this vertex. Okay, so this is very natural. So when you're making like some kind of communication network, the edge capacities typically reflect how many messages can go through some kind of cable or something. But the vertices represent switches or routers in a network, and the routers themselves often have a capacity constraint of how many messages they can process per minute, per second, stuff like that. Okay, so a lot of real-world networks will have both edge capacities and vertex capacities. Okay, here's another one. Another application we'll do. This is a very common problem. Okay, so what I've put up here is a bipartite graph. Okay, so in other words, I can divide the edge. The vertices are divided into left and right, and the edges are only going across these two sets. There's no two edges between two vertices on the left or between two vertices on the right. Okay, so a matching is a set of edges where the endpoints are disjoint. Okay? And the goal is to choose a maximum size matching. So I want to choose the maximum number of edges so that none of them are touching each other. Okay. One can also ask this question in general graphs, and in fact, that'll be a topic after spring break. Here we're focused on bipartite graphs. Okay. All right, so this one, I thought I'd open up the floor and ask, what is the maximum size matching in this graph? I'll wait a little bit so you guys can stare. Okay, so clearly the maximum is at most 6 because there's 6 vertices on each side, so that's an upper bound. All right, did anyone find 4 disjoint edges? Raise your hands. 2 people found. Did anyone find 5? A matching of size 5? Okay, some people found 5. Can anyone get 6? Got 1 6 in the back. 2 6s. Okay, if you got 6, then what are your 6? What I'll do is, I guess I'll point to an edge and you just tell me yes or no. Okay, so let's take this top edge. Yes or no? Yes? Oh, okay, well, there's some disagreement. I'm going with a thumbs up. So I'll add that. Okay, that means I can eliminate these 2 edges. I can eliminate these 3 edges because they're all incident. Oh, and also this one. All right, so those edges I can't take anymore. All right, so let me go down to the next one. How about that edge? Also a thumbs up, okay. Take this. That means I can't take this one. Okay. How about that edge? That's a yes. Okay. So I can't take these 2. Must be a faster way. Okay. How about that edge? Okay, just, I wonder if it seems like everything just works. Okay, we'll see. Oops, sorry. That means this one, these 2, can no longer take. Okay, we've got 4. How about, oops, I'm pointing from the right. How about that edge? Okay, I'll add that. That means I cannot take this one. Okay, and then I guess this one. That's a yes. Okay, congratulations, you got 6. And apparently all you have to do was take the first one you were offered every time. I don't think we ever said no to any edge. Okay, I thought it was going to be a little tougher. Anyhow, we got 6. It's clearly best possible because there's only 6 vertices on each side. Okay. What 6 did I have in mind? I thought I highlighted. Oh, no, I didn't. Okay. All right. Okay, so that's a matching of size 6. All right, so another problem is Same kind of input, but this time you're choosing vertices. Okay, so this is called the vertex cover problem. Okay, so a vertex covers a set of vertices so that you're taking at least one endpoint from every edge. So the vertices, in a sense, cover the edges, in the sense that a vertex will cover any edge that's incident to it. Okay, so the goal is to take the minimum set of vertices. This is a min problem. Okay, I'll give another minute for you guys to eyeball and see what the minimum size vertex cover you can find is. All right, so the maximum, I guess, is 12. You could have taken all the vertices. The goal is to do this smaller, though. I'll choose a number in the middle. Did anyone get 9? Okay, we got 1, 9. Did anyone get 8? Maybe this one's harder to keep in your head. Okay, so presumably nobody got 7 or 6. Okay, let's work through it together. Then I am going to point out a vertex, and you let me know if you took it. Okay. Okay, so I'll start with, I'll go from top down, left to right. So I'll start there. Should I take that one? Okay, no. How about that one on the right? No. But you have to take one of them because you need to cover that top edge. All right, so you guys pick. Should we take the left one or the right one? Either one's fine by me. All right, let's take the left one, which at some level means I've covered these 3 edges. Okay. I'm assuming you still don't want to take the right one, so I'll advance to row 2 on the left. Should I take this one? Well, if we're not taking the top right, I do have to take it now because there's that one edge. Okay. Do you guys want me to take this one? No? Okay. I won't. Let me put X's to remind myself. How about this one? Got a lot of nods. Why not? Okay. I'll take this. That resolves these 3 edges. Okay. How about this one? No? Okay. All right. How about this one? I guess this one you have to at this point. Okay. All right. How about this one? Mostly no's. How about this one? Okay. All right. And then how about this one? And then how about that one? Okay, good. We got all, okay. So in hindsight, we should have all been trying to get solutions of 6 or less, since obviously I could have taken everyone on the left or everyone on the right. But I guess the best we got was 9. Okay. All right. Which is, I guess, better than whatever I had in mind as well. Or no, that's 6. Okay. It's not so bad. Yeah, question? Okay, yeah, you can think of, yeah, so there's always this connection between two sat and graphs in some sense, especially because of two edges have two endpoints. Two sat clauses have two vertices each. I would say one difference is that in two sat, you just want to satisfy all the clauses. We're just sort of like covering all the edges at all. Here we have an additional element of this min. So the appropriate analogy for two sat would be like, you want to satisfy this clause, but say setting as few variables as possible to true. And all the clauses only kind of show that, yeah, so, and so there's a good reason, this probes at why you can actually solve two sat. It's not something we've explicitly discussed. And why you can actually solve this has a lot to do with this sort of parity going on. Once you get to three sat, that's enough degrees of freedom to do like assignment and stuff like that, and that's when the complexity explodes. Okay? Alright. Oh, it was that order, that was not matching. Okay. Alright, here's a funkier one. This is called the project selection problem. Okay. So the idea is that you have a bunch of projects, and they have some kind of net profit. So in green, they're all positive numbers because you get $4 for taking on this project, $2 for taking on this project. Other projects with negative net profits, those are like costs. You take on this project that costs you $2. You take on this project that costs you $4. Okay? But what makes this problem interesting is that we assume kind of precedence constraints. If I want to take on the $4 project in the top left, I first have to do the -2 and the -3 projects that it's pointed to. Okay, so I'm going to assume these dependencies are acyclic. Okay, and so my goal is to choose the subset of projects that maximizes the total profit, but I have to include any dependency. Okay, so here then is an example, and I'll give you guys half a minute to try to come up with a set of projects that includes all of its dependencies, but maximizes that sum of numbers. All right, did anyone find one that breaks even besides the empty solution? All right, how much were you able to get? 2. Okay, 0. Did anyone get more than 0? So I think if you take this set, it includes all the dependencies, and it's probably worth 2 points. Yeah. Oh yeah, so once I've taken the 4 and 2, I've already paid the -5, the -2, and the -3 automatically. And then you also might as well take the 6 if you had taken the 4 and the 2. Yeah.
Does the -3 get double counted?
It does not get double counted. So you just have to build that one once. Yeah. Okay. Sort of an interesting problem. Obviously useful. Oh. Okay. Okay. Here's another creative one. It has to do with trying to figure out if sports team can still make the playoffs. Okay. So Let's say that it's near the end of a baseball season. There's no baseball seasons anymore, but nonetheless. Um, and I want to know if the Boston Red Sox can still catch the New York Yankees. Okay. So I have two columns. One is how many wins they already have. Okay. And the other is how many games they have left to play. Okay. Now, okay, Boston has 2 games left. They can get up to 92 wins, and if everyone else lost all of their games, they can at least tie for first, in some sense, right? But what if those teams start to play against each other? Right? If Toronto plays Baltimore, somebody has to win. Okay. So, in addition to this, suppose I told you the remaining schedule looked like this. New York still has to play Baltimore and Toronto. Baltimore still has to play New York and Toronto. And Boston. Toronto also has to play everyone else. Boston has to play Baltimore and Toronto. Okay, so there's no tie. Somebody has to win every game. Okay. So now if I asked you, is it possible for Boston to make the playoffs? I'll ask a yes, no in like 20 seconds. Make the playoffs just means they tie for first. They get in the play-in. All right, anyone come up with yes? We got 2 yeses. Anyone come up with no? 3 no's? Okay, great. Okay, so we can say mark this up. So, I can assume, let's say, okay, so ideally maybe Boston wins all its games. That seems necessary. Okay. Now, I need also New York to lose all of its games. So I will give that game to Baltimore and Toronto. Okay, so sort of confusing, but we've already eliminated those games. Okay, so this is just to make sure that Boston gets as many as possible and the Yankees don't win anymore because they already have 92, so those are necessary. Okay, but now we're left with Baltimore and Toronto now each have 92 wins, and there's 1 game left between them. So whoever wins the Baltimore-Toronto game will get the 93rd win. Okay, so it's actually impossible for Boston to make the playoffs. Okay, and of course we want to automate this on a much larger version of the problem. Okay. More problems. Here's a standard one. Assignment problems. So you have a set of m individuals drawn as stick figures, and you have n jobs. I didn't know how to draw a job, so I put squares. And at some level, you want to assign people to jobs. Okay, but the catch is that not everyone is qualified for all the jobs. Okay, so maybe you're given a matrix that encodes with 1s and 0s, whether or not a person is qualified for a particular job. Okay, and the question is, given this info, try to fill up as many jobs as possible. This was actually something that motivated a lot of this stuff when they're doing like allocations in the World War II. Okay. All right. More problems. This one's pretty cool. It's called edge orientation. I give you an undirected graph. Okay. And your goal is to turn it into a directed graph. For every undirected edge, you choose a direction. But the goal is to minimize the maximum in degree. Okay, so I don't want any single vertex to be the endpoint of too many of those directed edges you've made. So, for example, in this graph, here would be a solution where I believe every vertex has in degree at most 3. Okay, so I have assigned arrows to all the edges. Now it's a directed graph, but if I did it correctly, every vertex should be the endpoint of only at most 3 directed edges. Okay, so it's sort of a load balancing problem. Okay, so that's another one. I think this is the last one on the list. This one's pretty cool. I worked on this. The densest subgraph problem. Okay, this is often used for people analyzing social networks and stuff because they want to find communities. So I don't think we've used this term very much, but in general, the density of a graph is defined as the number of edges divided by the number of vertices. Okay, so if this was like a friendship graph, this is sort of like how many friends do people have on average, maybe multiplied by 2 or divided by 2 or something. Okay. So it's the average degree divided by 2. So the problem is to try to find a subgraph that's very dense, a very high ratio of edges per vertices. Anyone have a suggestion for a dense subgraph? Yeah. Okay, yeah, so I planted a complete graph between 5 vertices right in the middle. That may or may not. That's pretty dense. It's as dense as a 5 vertex graph can go, so it might be the densest subgraph. I'm not 100% sure. Okay, so of course, if you find a very dense subgraph in a social network, that's suggesting some kind of cluster of people that tend to know each other. Okay. All right. That's all the problems I have set up for us. We have a little time left to solve them. Okay. All right. Okay, I think maybe some of you guys have already done vertex disjoint paths in your PSO, so I'll go pretty quickly. Does anyone want to quickly volunteer how to model vertex disjoint paths? Yeah.
You can just replace that vertex you have right there for all the vertex in the graph with an in vertex and an out vertex.
Yeah.
Between them, the same capacity as the original vertex.
Perfect. Yeah.
Is the difference between an edge between in and out and one between out and in, or something weird like that, but for the most part it's the same.
Okay, yeah, okay. So the idea is that I know how to deal with edge capacities. I want to reduce to that. We split the vertices. We've used this trick for other problems before. One thing that might help you is that you can always, these edges themselves effectively have infinite capacity. I can use an original edge as much as I want. So one thing that can make your life easier is to add infinity. That's kind of allowed, or arbitrarily large number. And that'll also make sure that the minimum cut will always avoid those edges because it'll never want to take an infinite edge. That'll make some of the mapping easier. Okay, so that's just a warm up. I think you guys, half of you have probably seen anyway. All right. Let's look at matchings. How can I try to use flow to find a maximum matching? Any ideas? So I know how to pack paths, and now I want to take edges. Sorry, none of these, it's not at all clear that these are easy to guess. Once you see them, you'll remember them forever, but yeah. The inverse of a path that goes through all the vertices. I guess I'm not 100% sure what that means. Yeah, so you want many paths. So, okay, there is some opposite thing. A Hamiltonian path, I would have kind of wanted to find one small path that covers a lot of stuff. Now I'm kind of looking for a lot of paths that are kind of unrelated. Yeah. So that's like, yeah, we're going to do some kind of flow thing, yes. Or I say, yeah. Okay, so yeah, so all these problems, we're going to do some kind of auxiliary thing, so we'll often introduce an S and a T. Okay, that's first step. Yeah. Okay, so in that example, are you imagining flows that kind of are going like this or something? Oh, this starts to look like the Hamiltonian, like a ladder, maybe? Or maybe not. Yeah, so some level, if somehow kind of, if I take this edge, which is maybe like routing flow on that edge, I should not be allowed to route flow on these other things. And there's also this issue, yeah, there's a lot of disconnected stuff. I mean, S and T right now are not touching anyone. That's obviously an issue. There was really a suggestion here? No? Yeah. Oh, okay. So that's a reasonable idea. We just had vertex capacities. We can use that from now on. Okay. But this is at least kind of making some sense from a packing point of view. You know, capacities, I can only take one. And the main constraint is that I can only take one edge incident to each vertex. Yeah. Okay. All right. Now I'm sending flow from left to right. Okay. I want to make one more modification to this. I'll give you guys one chance to guess. Yeah. Yeah, just direct all these edges. Otherwise, you might get weird stuff that's zigzagging back and forth. You don't want that. Okay, so let me add all the directions from left to right. Okay. So now I can only look for paths going from left to right. This is very simple, and each one uses some edge in the middle. And I can only use each endpoint once for my vertex constraints. Okay. All right. Somehow the idea was that thing we're taking needs to be mapped to a path. All right. So if you have a matching, that tells you which paths to take from left to right. So when you actually do a reduction, you just need to double check both directions. When you have a matching with 5 edges in the middle, that tells you which paths to take from left to right. If you're given 5 paths going from left to right, rip out that middle edge. And they'll be disjoint because of those vertex capacity constraints. If you didn't want to use vertex capacity constraints, you could instead put 1 on those edges that are leaving S and entering T. that will have the same effect. All right, fun? How about vertex cover? It's a little weird because we're no longer doing a max problem, we're doing a min problem. All right. So for vertex cover, you can do the same thing. Okay, so I guess I probably should have added some arrows. Okay. All right, so if I find, so I'm going to set up the same graph and now look for the minimum cut from S to T. Okay. One thing different I did was I went ahead, I made the middle edges capacity infinity. Somehow we could have done that in the last problem because it's still bottlenecked by the outside ones, but that'll make sure the cut avoids any of those edges. So, what's the right way to look at this? Okay, so is this one going to be too messy to come up with something? Okay, so here would be an example of a cut, not necessarily the minimum cut. But if I delete those 5 edges, and I delete 2 edges from the right. Okay, so that's a cut of size 7. We know there's a cut of size 6, so it's not the minimum solution, it's just more interesting this way. Okay. Now, this makes sure that because it's a cut, there's no path left going from left to right. Okay. But in terms of kind of our vertex cover problem, that means for every of those original edges which are in the middle, which threatens to give us a path, I must have deleted one of those, either the S edge or the T edge for the corresponding endpoints. Okay. Which now, so the corresponding vertex cover to this cut will be those vertices. Okay. So making sure there's no path from left to right because I deleted one of those edges corresponds to sort of taking one endpoint of every edge. Because in our construction, there's sort of this one-to-one correspondence between S to T paths and edges in a bipartite graph, the input graph. Okay, so taking one endpoint of every edge means either deleting that initial edge or that terminating edge for every path. Okay, so this example is maybe less interesting just because the solution is 6 and you just take everything on the left or everything on the right. Okay, but the real correspondence is that there's every cut based on the edges you take will give you a vertex cover of the same size. So then you just minimize it with a black box. The minimization ones are always a little weirder. Okay, this is probably the craziest one. Okay. Project selection problem. Again, every project is associated with either being a profit or a cost. Costs are negative numbers. I want to choose a set of projects, maximizing the net profit. It has to include all the dependencies. I'll open the floor just a little bit, but this one's probably the most indirect. Yeah.
Just to shut the circuit here, can you separate out and give edge weights to like 2 edges, like change the weights and
I think it's a sufficiently generic description where it's not wrong. We'll assign capacities and we'll run max flow. So actually, in the mapping, we are going to do, it's going to ultimately be based on the minimum cut though. Well, of course, we'll run max flow, but the solution will relate to the minimum cut. Okay. And I want to somehow make sure that I don't break up any of the dependencies, if that's a hint as to how to assign capacities. Yeah. Okay. Okay, yeah, so we are going to set up some, okay, let's just see what it is. Okay. Yeah, okay. All right, so here, this is sort of similar to what you were saying, maybe, kind of. I guess my example is a little biased because it looks like the profits are always on one side and the costs on the other, but it could be more intermixed. There could have been costs that depend on profits, depend on costs. So this is sort of a oversimplifying picture, nonetheless. So what have we done? So one thing already to point out is that we were dealing with negative costs, and we have no idea how to deal with negative numbers in max flow. That it just never came up, and it doesn't make much sense. So what we see here, though, where the asymmetry enters, every profit has an edge from the source, with the value of the edge equal to the profit value. Every sink has an edge to, every cost has an edge to the sink, where the capacity is equal to the cost. Okay, so somehow the sign is getting snuck into whether or not you're connected from the source or connecting to the sink. And one thing we've done is we've added positive infinity capacity to all the dependencies, which will at some level make sure that I never break up any of the dependencies. I don't want to kill those edges. Okay. So the claim is that computing the minimum cut will give you the best project selection, but sort of the value of the cut compared to the project value is going to be a little bit funkier. So let me, as an example, highlight what we believed was the best solution before, which was this. Okay, so that we thought that those projects gave you a score of 2. Okay, so the claim is that this should give us a minimum cut in the graph. Let me draw it better so that it's not intersecting things. Let me also use a different color. Okay, so let me. Okay, all the purple edges should be positive infinity. I forgot to label a couple of them. Okay, so the S to T cut, I'm only worried about the edges that are leaving the S side and going to the T side. One thing to keep in mind. So let's look at the edges in this cut. So first, for every profitable project I don't take, I pay 3 for that one. So every profitable project, I pay something proportional, equal to the profit value. And for every cost project I take, I pay the cost. Okay. So the cost of this cut is exactly the profit of the projects I don't take plus the cost of the projects I do take. Okay. And in general, I want to not leave out much profit. I want to take as much profit as possible. So I want to minimize the profit I leave out. And I want to also minimize the costs I take, right? So I want, and that's, so you also see that appearing in the cut. Okay. So that means that the cut capacity of whatever ST cut maybe I can copy a picture just so. Okay. All right, so the capacity of a cut is equal to the cost, no, the profits we don't take, profits we leave out, plus the costs that we do take of the costly projects. Which is equal to, I can write this as all possible profits minus the profits we do take, right? So the profits we leave out are equal to the total profits minus the profits we do take. They all add up to something. And I'll leave in the cost that we take. Okay. So this is all possible profits minus sort of net profit, profit minus cost of what we take. Okay. So by minimizing the ST cut, I'm ultimately maximizing the net profit of the projects we take. Yeah.
Is there something weird going on with the graph? The edge of weight to the project that's a dependency?
Okay, so one thing that the dependencies do, right? So my cut will never want to take a dependency edge because the capacity is infinity.
Yeah, but instead of taking the 5 cost edge, we take the 2.
Instead of taking the 5, this edge. So it would much rather take that edge than this dependency edge because that would cost infinity. That would kill you. So by making sure, by giving maximum possible capacity to the dependency edge, I make sure my ST cut never kind of breaks the dependency, so to speak. It'll never take an edge and split up dependent projects. So ultimately the projects I'm going to take are the ones that are on the S side of the minimum ST cut. This is the weirdest one. You'll want to double check this. All right, let's keep going. All right, playoff elimination. You want to know if the Red Sox can still make it. And the real input is something that looks like this. How many games are left between every team? Any ideas for how to model this as a flow problem? This one's also pretty creative. Maybe one thing to keep in mind is you have to distribute the wins. Yeah.
And we set it up as like a bipartite graph.
Okay. So if it's bipartite, there's something on the left, there's something on the right, and you're probably putting S and T. You're doing some setup like this.
Yeah, and then like the matchups are what go between the two sets.
Okay, so each of these should be teams, you're saying?
Yeah.
Okay. Okay, so in this model, each pass should consist of probably a win going from one team to another.
Yeah.
So if I'm looking at like New York versus Baltimore, who is giving who the win?
I guess maybe the team on the left would win.
Maybe this is. But so there's a little bit. It feels it's just hard. It feels like there's some symmetry teams and teams, but then there's there's a slight mismatch. Yeah. Okay. If I did games, and imagine, so I have one vertex for every game with vertex capacity 1, or maybe the source edge has 1. I can think of that as having to distribute one win to one of the teams on the right. Okay, so here then is the full, what the full construction is going to look like. So this is essentially a bipartite graph with your source and sink added. So in the left, I have one entry for every game. Okay, and the source vertex has 1 because it wants to, there's only one game to give out, one win to give out for every game. And so I've drawn an edge, for example, from the New York versus Baltimore game to New York or Baltimore. Either one can win. But maybe the key point is that on the right, what I'm saying is, look, if I want Boston to make the playoffs, I can't have New York win any games. So I put the edge with capacity 0. Equivalently, there's no edge. But to make it clear, I put an edge with capacity 0. I don't want the Yankees to win any games. So that's why it has capacity 0 going to T. I'm allowed to let Baltimore and Toronto win at most one game before it gets to 93. 92 is okay. So that's why I've added an edge of capacity 1. I only want to allocate at most one win to Baltimore and Toronto. And then I put no capacity or infinite capacity on the Boston edge because I want it to win as much as possible. So now what I'm asking is, can I get a max flow of size 5 in this graph? The max flow of size, a maximum flow that allocates wins for every game, but allocates at most one win to Baltimore and one win to Toronto, and 0 wins to the Yankees. Right? Which we know the answer is no in this. So the algorithm here would probably compute a flow of size 4. It would fail to come up with a way of making sure every game is decided, but Boston still makes the playoffs. Okay, so maybe the new trick here is that the edges on the right limit a capacity of how much wins I want to allocate to each team. So it turns out to be sort of a clever allocation problem. There's a lot of allocation problems that can be solved by flow, where one path corresponds to allocating one item. Okay? Alright, so the generic construction, games, teams, and then have a capacity for how many games I want to let a team win at most. Check to see if I can route all the games, so to speak. Alright. Here's the putting people in boxes problem. We have M individuals and N jobs. Not everyone is qualified for all jobs, and I want to fill as many boxes or cubicles as possible. So I give you a bunch of 1s and 0s to encode this information. Or I could have given you a list or whatever. Okay. For this problem, How can I model this as flow? This might be easier than some before. Yeah.
So you would have the workers on one side, the edges, so thinking of bipartite graph, on
Okay.
being the workers, the other side being the jobs, and then the edges being the qualifications.
Perfect. Okay. So we'll set up a graph like this, where each person can get allocated to at most one job. That's why I put a 1 there on the left. And I want to get one person for every job. That's why I put 1 on the right, or at most one person for every job. And the purple edges are only where the individual is qualified for the job. And this is actually also essentially a bipartite matching problem from before, where each of the middle edges of a qualification represents matching up a person to a job. That's where the name matching comes from. Okay. I only point out that, it's completely natural to be like, oh, this job needs 3 people, the next job needs 4 people, this person can do 3 jobs, and so forth. And you can adjust those source and sink edges accordingly. All right. Our timing is pretty good. Okay. Edge orientation. I want to assign directions to all the edges. Some people might have done this in their PSO yesterday. I don't know if they got there. Or Tuesday. I want to assign directions to the edges to minimize the maximum in degree. So let me instead pose this as a decision problem. Suppose we guessed the in degree that we're going for, and afterwards maybe we can do binary search to figure out the best one. So suppose I said, okay, can you find an orientation where the maximum in degree is 3? So you want to use this number 3 in whatever you're going to construct. How can I model this as a flow, cut, edge, disjoint path problem? Yeah. Okay, are you proposing just a greedy algorithm altogether? That will, there's lots of counterexamples to this. There's a reduction to flow though that'll get it exactly. The greedy algorithm is a natural thing. I think it might get you a factor 2 approximation, if I remember correctly. But there is a better way to do this with flow, which may be slower. Sometimes people do the greedy algorithm in practice if speed is an issue, even though it doesn't work. Yeah.
Is there a way that you can connect, like, overlapping vertices with 3 in degree to the out?
Okay, you want to connect vertices to T. So one thing keep in mind, there is no in degree yet. I mean, that's on the rule. Maybe this example is not sufficiently hard because there's so many low degree vertices. I imagine something more complicated. Okay, so if I said the question was I want to assign to every edge a direction. keyword being assign. Yeah.
Well, assign makes me think.
Okay, we'll make a bipartite graph. Then what's on the left? What's being assigned? Oh, okay. What is individuals get assigned to jobs? So what would be the individuals in this? Okay. Okay, so the vertices are the individuals, and then I want to assign direction. Okay, so I have this vertex. I want to assign it. Okay. So an individual might be an edge, and I want to assign it to one of the two endpoints in a way. A direction will map to an endpoint. Okay, so that's going to be our construction. Okay, it's one of my better pictures. Okay, so here's a bipartite graph. So everything on the left corresponds to one edge. It might be hard to see, but one of those edges are more darkly shaded in each of those pictures. Okay. And, okay, so this edge in the middle is between those two vertices that are barely highlighted on the right. So that's why I draw those two edges. This edge has those endpoints. This edge has those endpoints, and so forth. Okay, so every edge in the input graph corresponds to an individual being assigned a job. Every endpoint corresponds to a job. I want to allocate each one. Okay, and whatever my target value is, if it was 3, I would have put 3 here. In general, it's some h, where h is the in degree I'm going for. If I can test one value of h, and I can do it, then I can try decreasing h or increasing h or whatever, and I could do binary search as well to limit my guesses for h. If I can do it, divide it by 2. If I can't do it, go up by a factor. Not doubling, but halfway to whatever it was before. Okay, last one. Trying to find the densest subgraph. This one's kind of hard, I think. Okay, so in the interest of time. So the densest subgraph is going to use the same construction, where I'm going to try to assign edges to endpoints. But now my h is, let's say it's whatever target density I'm going for. I'm just trying to decide, is there a subgraph with density greater than my value h? Or are all the subgraphs have density less than or equal to h? Okay. Actually, it's probably better here to put positive infinity, because there's going to be one of the min-cut applications. Let me explain the claim. I'll only do it at a high level since we're roughly out of time. Okay. Okay, so we'll make this infinity. Okay. All right, so the claim is, if I have a flow of size m, and I can route all the edges and assign all the edges to vertex endpoints, but within degree at most h, then the density is at most h. Okay. Why? If I have some subgraph, right? If I have some subgraph, and I was able to orient the edges so that everyone has in degree at most h or something, that also tells me, that gives me a bound on the in degree of every vertex, which gives me a bound on the density. So if I can orient the edges so everyone has in degree 2 or something, at most 2, then the density is at most 2 of that subgraph. Okay? But if there was a subgraph with density more than 2, then it would be impossible for me to orient the edges within the subgraph so that everyone had in degree 2. So in that example of this star, okay, and I said and h was equal to 1. Just focusing on those red edges, it's impossible to orient those red edges so that everyone has in degree 1. You can do 2, but you can't do 1. Okay, so actually there's a very close connection between density and orientation. So if you cannot route, and you can check this, I'll put in the notes. If you're not able to assign all the edges to an orientation, then you'll get some ST cut that will naturally look like this. It'll delete some edges here and some edges here. Okay, and I believe that these vertices corresponding to the cut on the right-hand side, that will give you a subgraph with density greater than h if you're not able to route everything. And you can check this calculations. Because at some level, those were the ones where you weren't able to fit in kind of the edges, so to speak. Okay, so that was the last example. It turns out that densest subgraph and edge orientation are also primal dual problems to each other, although that's more complicated to show. That's why there's this strong connection. Okay, that's fun. And that's it. Have a nice spring break.